Hello, welcome everyone to the Predictive Healthcare Speaker Series. This instance of the series is one I'm particularly excited about. We normally think about predictive healthcare as producing, using data and machine learning to produce predictions about individual patients, so we can take actions to improve their outcomes. What you're going to see here today is something a little bit different, where we've modeled entire complex dynamic systems to try to make predictions about those systems and actions taken at the system level rather than at the individual patient level, using something that's often referred to as a digital twin or a simulation of the system. So I'm not going to give any big long intros. I'm going to let the speakers take it away. We have a few really good speakers today. Dr. Hemmert, Asaf Hanish, and Susan Regley are going to, for the most part, take us through today's presentation. We're using the live events version or option in Microsoft Teams, and it's my first time producing such an event. So hopefully everything goes smoothly and people can post their questions in the chat, and we'll have some time for discussion at the end of the presentation. Okay, I'll pass it over to Asaf.
Hey everyone. So first of all, can you hear me and can you see the slide number 2? You can, I don't know if you're muted, but you can clap or thumbs up or something, or just let Corey know that we're good. And if you, I think we're good. Okay. So digital twin is our decision framework for supporting the HUP-ED. So what's a digital twin and what do we think about that? Well, we're thinking about it as a simulation, a virtual representation of the real thing. So, the real HUP-ED is made up of humans and bricks and HVAC and a lab and all that stuff. Our virtual representation of that ED is Python code and data distributions. And so the digital twin, it's really a tool that's used to make operational decisions, and it's used in a pretty widespread fashion among a lot of industries, including aviation, oil, gas, power. Really quite a reliable, quite a well-used tool. And the reason to use it is to increase reliability and availability of services, to operationally improve performance, manage risk, manage KPIs, which are key performance indicators for value. And it's really a good tool to be used when modeling a complex or dynamic system. And the reason that it's such a good tool is because the system is a bit more complex and you can sort of reason through in your mind. And a representation of all of that through a schematic, through data, can help make better decisions. So in this talk, we're going to talk about what is the HUP-ED, give you an introduction in case you're not familiar, talk about the HUP-ED's challenges and why we think the digital twin is a good fit for it. We'll talk about the digital twin, what it is, how we built it, how we validated it, and how we've used it recently to make some decisions, understand our operational system and make some decisions, and talk about what we feel would make for a successful project, sort of the prerequisites for a good team and a successful project to really get value out of a digital twin. So with that, without further ado, here is the HUP-ED.
Thanks, Asaf. My name is Keith Hemmert. I'm one of the emergency physicians at HUP and in the emergency department there. And I also serve as a medical director for our department. Thanks for having us here today. It's great to be able to speak with you all. So I want to just briefly familiarize everyone with HUP and with the emergency department. Many of you in the Penn community may already be somewhat familiar. It's a massive quaternary care hospital, 776 licensed beds, a #1 ranked hospital in the state, and #15 in the nation, based on U.S. News and World Report. We provide subspecialty quaternary level care, meaning we do things at this hospital that only really a handful of other hospitals in the country do, whether it's heart transplants, liver transplants, novel therapies for cancer. Really the most advanced care in any medical subspecialty is happening at our hospital, which means as a result that we have a very high acuity with lots of very, very sick patients. Like basically every other academic medical center, we have a tripartite mission, the first and foremost being the excellent delivery of clinical care to our patients. The second being supporting a robust educational environment. You know, there's a medical school, of course, associated with the hospital. We have medical students, trainee physicians called residents. We have fellows, we have nurses, nursing students, mid-level providers. So the hospital itself is a complex environment with a lot of educational demands on it. And then, of course, the third leg of the mission is research and ensuring that in addition to the delivery of clinical care, we continue to support really world-class level research so that we can deliver those cutting-edge therapies that make our university hospital so distinctive. In terms of executing on the mission of the delivery of clinical care, there are a couple of key values that we talk about that really drive our decision making and our planning in the operational world. One of those is access to care, which is pretty straightforward. It's, you know, can people get care when they need it? Can they get it promptly when they need it? And being in the emergency department, that's something that I think about quite a lot. When people require access to emergency care, can they access it when they need it? The next thing we think about is the timeliness and efficiency of that care. Not just can people access it, but along their care pathway, is the care that they're receiving timely? Is it efficient? Are there delays that obviously negatively impact both the care they get and the experience that the patient has? And then finally, quality and safety. Obviously, we want to do everything we can to ensure that the care that patients get is of the highest quality with maximal safety. And there's clearly some overlap amongst those core values. Our department in particular sees about 60,000 patients annually, which translates to between 150 and 200 patients a day. We have one of the highest case mix indices in the nation, which is a marker of acuity, but there's a simple way of saying we see extremely sick patients in our emergency department. As I mentioned, it's a complex environment in many ways, both in terms of personnel. We have attending physicians, resident physicians, mid-level providers, students of various sorts, technologists, so on and so forth, all performing complex workflows, seeing patients, admitting them, discharging them, getting labs ordered, labs performed, radiology performed, consultations to the patient. So as Asaf was hinting at, it's a complex environment that certainly poses challenges when it comes to modeling. If we can go to the next slide. So with regard to those core values that I was talking about, we have to figure out ways to measure whether or not we're succeeding on those core values. So when we talk about access to care, the way we measure that is a metric called left without being seen. And what that means is how many people showed up in the emergency department and then subsequently left before they saw a physician because the wait was simply too long. The national benchmark for this is about 3%, which is, when you think about it, a high number. That means on a busy day when we see 200 patients, that's 6 patients leaving without getting care. And based on the acuity of our population, those would probably be 6 pretty sick patients. So one of the things we try to do is minimize that number. When it comes to the value of timeliness of care, we measure that with how long does it take from when the patient shows up in the department until when they see a physician, a door-to-doctor time. A national benchmark for that is about 30 minutes. So again, can you see a doctor when you need to see a doctor? And finally, efficiency of care. When you're in the department, how long does it take to get your care done? So how long do you stay in the department? We measure that with the length of stay. It's fairly straightforward. There's a couple of challenges to executing on that mission. Aside from the obvious challenge of the pandemic for the past year, in general, the hospital runs at very high capacity. We routinely run between 90% and 105% capacity in the inpatient side of the hospital. And that has a trickle-down effect to the emergency department, where as a result of the hospital being full, it's difficult for us to get patients admitted out of the emergency department upstairs to the hospital. So our emergency department fills up with admitted patients boarding in the emergency room. On a busy weekday, in fact, I can tell you right now, of our 40-bed emergency department, we have about 35 of those beds being used for inpatient care rather than true emergency care. So on any given day, somewhere between 50%, 75%, obviously today it's even higher, of our space is being used for non-emergency department care. That's a challenge that we can't control. I can't force the hospital to open up inpatient beds. So the question we'll come back to in a minute is, how do we confront that challenge? The second challenge is space. We can't expand our footprint. To build a new emergency department is a massive undertaking. That's sort of a segue to the next point, which if you've been physically on campus anytime in the last 5 years or so, you'll have seen the new tower going up across the street from current HUP, which is scheduled to open for business in October, and we're moving in there in October. So it's a very exciting time. But, you know, for the past several years, we've been trying to figure out how do we confront these challenges that I just described and execute on our mission with the constraints that we have. Next slide, please. Thank you. So one of the main things we can control is our workflows. So we've done a pretty substantial revision of our workflows in the past several years so that we have a provider near the front end of the emergency department so that patients can in fact see a doctor within 30 minutes. Last year, we managed an average of 26 minutes. We started segmenting care rather than all patients of all acuity going to the same section of the department. We segmented care very, very early after patient's arrival and segmented the lowest acuity patients to one care track, mid acuity patients to another care track, and the sickest patients to a third care track. And if anyone's familiar at all with queuing theory, you'll recognize that essentially what we've done is create more servers in a care pathway to minimize queue times. Part of this also involved recognizing that not every patient requires being in a physical bed for the duration of their emergency department stay, and they can spend some of their visit waiting in a comfortable semi-private waiting space, and therefore we can make more efficient use of the exam rooms that we have. So we're essentially creating virtual capacity. Integral to the question of workflows is the question of bed and staff allocation. Once you've created these workflows, the question is, well, how many beds should you allocate to your fast track, or how many beds should you allocate to your mid acuity track or your high acuity track? And likewise, how much staff should you allocate to each of those locations in order to both maintain quality safety, but also minimize those numbers of door to doctor time, length of stay, and left without being seen, which again represent sort of those core values that we're trying to execute on. I'll speak very briefly about financial impact. You know, for me, this discussion really centers around what's the right thing for the patient and how can we best deliver care for the patient. But it would be short-sighted not to acknowledge that these decisions also have substantial financial impact. The revenue and cost equation in emergency medicine is pretty straightforward. You know, we bill for the care we deliver to patients, but the volume of patients that show up in the emergency room is beyond our control. So we need to minimize the number of patients who leave without being seen, because every patient that leaves without being seen is essentially revenue that is escaping us. And our primary cost is staffing. You add more docs, nurses, residents, what have you, and you're spending more money. So the impact of minimizing left without being seen, minimizing length of stay, and coming up with the most lean staffing model that maintains quality and safety that's going to be what allows our department to run in the black. So we'll go to the next slide, and I'll just briefly start this off by saying, you know, in order to figure these things out, what's the balance of beds and staff and where people work? It's very difficult to predict what that balance is. And in the old days, we did real life experimentation to try to figure out what if we created a novel unit over here, we'll dedicate 10 beds, 1 doc, 3 nurses to a new style of care without really being able to predict whether or not it would work. And as Susan's going to talk about, the cost of doing that is very, very high. So I'll turn it over to Susan.
Thanks, Keith. And I just want to, I'll give a little handoff communication here. For those of you on the call, we have realized that the Q&A is not visible to people. So we're going to use some back channels here. If you can message, if you're internal and can message Corey Chivers directly, you can send questions to Corey that way. Or if you cannot get access to that, you can email him at corey.chivers@penn.upenn.edu. And if I'll repeat that once more just in case, corey.chivers, CHIVERS, @penn.upenn.edu. Because we do want to encourage conversation, but as Corey said, this is the first time using this particular platform, and it's not set up to accept Q&A. So. Okay, so to go on from what Keith was saying, usually when we do a project, I, from the human factors and human computer interaction side, do observation of what the process is that we're trying to improve. And so in this project, I will mention we did do some early observation of the actual ED flow and sort of use that to define our problem space and what were the areas that we thought were most ripe for improvement. But what we're really looking at here, the process that we're trying to improve is really the decision-making process in this case. And that's a little bit different from the digital twin versus other projects that we do, where we're trying to identify specific patients, as Corey mentioned. So the old process mapped out here is that somebody like Keith would, using historical data, their best guesses, they would play with and interact with the data a lot and choose 1 to 3 options for staffing changes, talk to them with stakeholders, talk about them with stakeholders, and then they'd possibly use rapid experiment test days with the chosen options. And the important thing here is that these rapid experiments are really a resource and political capital drain. So this means changing people's schedules for a few days. This means potentially, if the change causes problems, creating very difficult days for people. And so the process of convincing people that this is the right thing to do is a drain on multiple resources. And then the outcome of those rapid experiments, they would present a proposal and data to strategic ops group. But you're talking about then presenting a small data set with which is highly susceptible to outliers. So if you run something to 2 to 3 days, you might get one day where something happens that's unusual. And so it's very hard to think of this as a representative set of data. And then the new staffing model would be implemented. Using the digital twin, several advantages here. One is that you can run tens of experiments to choose the best option very rapidly, experiments using thousands and thousands of virtual patients. And you can test variables that you couldn't previously test. You can discuss those experiment outcomes with your stakeholders, choosing the best options out of multiple tested options. And then you still want to run the in situ experiments, the live experiments. But here you have a lot more data to assist you with persuading people that it's worth running these experiments and it's worth changing their schedules and taking that risk. And then your outcomes of that, comparing the rapid experiment, which still might have outliers, et cetera, but you're now comparing that with your simulation outcomes. And so you have a much more solid case grounded in a lot of data before you go to your strategic ops group and decide to implement that new staffing model. So next slide. So just to summarize some of the main challenges, real world experimentation is usually disruptive. The decision makers have limited data that they can look at. A lot of times, anytime you're working with hospital data, you have potentially poor quality data. And it's difficult to balance all the multiple priorities in your head as you're doing that decision making. There's just more than you can handle and analyze at once in terms of the priorities. So we want to try to improve that decision making process, to leverage data, to increase our confidence, to make better decisions, and overall to increase the buy-in from the team. So really we're looking at reimagining that process to bridge the gap between somebody like Keith's intuition about what might work, and then that boots on the ground experimentation where we kind of see if it sort of does work, to put this into something that's more rapid, that's more grounded in a larger amount of data, that's not disruptive, or at least that is, it's just less disruptive in terms of trying out multiple different options. And in order to do that, we created a digital twin and did run experiments to assess that real world impact in the HUP ED to demonstrate that value. Next slide. So I'll start this one off just summarizing then our operational goals to optimize resource allocation in the HUP ED, in terms of process and in terms of staffing. And there we are looking to improve values such as quality, equity, and access, and patient experience. And I will say that equity and access is one of the main Penn Medicine goals this year. And so this is an extremely timely process from that perspective. And I'll pass off to Asaf for the rest of this slide.
All right, thanks, Susan. So yeah, as Susan was saying, the goal is the operational goals are sort of the thing that sit on top of this pyramid that we aim to answer, and so we step down down this path, answering progressively more granular questions in order to support that. And so if our goal is to optimize the ED and to improve quality and equity and access, then the things the levers we can change, as Keith was saying, is the staffing and some of the configurations. And so what we're going to do is answer those questions. What are our staffing challenges, and how can we change those things around to impact wait times? How would those changes impact left without being seen, or if there was a change in the arrival pattern of patients, how would that impact left without being seen? Those are operational questions, and so in order to answer those questions, we actually have to dig even deeper and start answering some validation questions, which is, do we have a model that can replicate this? Can we recreate some of the key metrics with a model and with our data that we have? And if we can do that, we can answer operational questions. If we can answer operational questions, we can answer operational goals. So that's sort of the raison d'etre for what we're doing here. All right, so I'll walk you through more details about our whole process for a simulation, and I represent this as a life cycle, starting in the upper left and going clockwise. And the reason I do that is because we believe this is a part of a process of continual improvement, where we're constantly refining. So it's a bit of a busy slide, but let me just get started. So this starts with a group of people who have a particular goal in mind for improving something, and it's got to be granular. And so for us, we actually sat in a conference room, a while ago, and thought of the thing that needs to be improved is the left without being seen rate. And the way we can do that is actually by shifting staff and changing hours. It has to start there, because if there's no direct question, then there's no further build that can happen. So we have subject matter experts and area leaders driving a definition of success. What's the KPIs and what's the levers that we can actually move? And they're going to work with the data scientists and data experts to drive that. Once we have that ideation, that idea of what we're trying to do, we have to design something in detail about how we're going to, what that process looks like. So we need a really good detailed process diagram that captures the complexity of the situation. So we have subject matter expert working with a data scientist and an area analyst just to map out this whole process. And one of the challenges is to be able to elicit the right kind of information and the mechanisms that can be abstracted into this diagram that we can then fill in. So how do the patients flow? Where do they bottleneck? Let's build all the steps. That's 2. Number 3 is we have to understand our data really well. We have to be able to represent our data in numbers. So patients don't just show up, they show up at some pattern. So the graph you're looking at is actually the average arrival pattern through the week, and you see a diurnal pattern peaking in midday, troughs in the evening. A data scientist and a data expert will have to define where this data lives, how to pull it in the best way, and then validate it that it is correct, the distribution is good. Once we have that, then you start coding. So our product, the digital twin, it's written in Python, and it's got functions and classes and data dictionaries and distributions that represent those mechanisms in a design and the data distributions in our understanding stuff. Once we've built that, then we have to validate that the results that come out of the simulation, so at base level, can match what is real. So the graph, if you are able to see it, has two lines. One is the average arrival pattern as we observe it in our data, and another line that is the simulated results from the digital twin. that show that we can recreate arrival patterns and other things, wait times, census, all those sorts of things. And so what it's a cycle, and then we can then go ahead and ask yet another question and perhaps kick off yet another design process. So some of the, just diving even deeper into the simulation, here are some of the agents in the simulations. An agent-based simulation, there are actual bits that move around and interact with each other. So we have patients, we've got staff, we've got beds, we even have managers. And so a patient is, at base level, is someone who is a representation of a person's need and the pathway that is optimal for them. So those are the things we encode. So on the left, we have top left, we have a patient. This is the 13,000th patient in our simulation. They arrive at a certain time in a certain mean. They have an ESI, which is a indicator of their severity, how sick they are, which represents then the kind of needs they would have, what unit they should go to, that pathway that Keith previously showed. There's the acute level, the forward flow, or the fast track, depending on their acuity. And so that's their need. Whether or not they should see a PIT provider in triage, which is a role that is part of the pathway. And then how much care they need, and whether or not what's the amount of time they are willing to wait in the waiting room before leaving, left without being seen. And so all those things are sort of gathered up from historical data and assigned to patients at a pattern. There's a pretty heavy randomization component in as well. There's also staff, different staff working at different places. The beds, they have the different times where they're open and closed to represent the real HUPED. And the most difficult challenge is for the manager. And so the manager is a concept we have come up with for the rule sets that govern the pathways. So when a unit opens and closes, should the unit close early because there are so many patients in it that they won't, if the unit is supposed to close at 11, would they stop allowing patients to be bedded at 9 or 8? All those sorts of things that a human manager might decide. We sort of encoded those things with some decision rules as well. And so those are sort of the agents in the simulation that interact with each other. Okay, so an even busier graph. It's the representation of the HUPED at a high level, the simulated HUPED at a high level. And I'll just sort of walk you through a little bit of it. I don't expect everybody can, I don't know if you can even read, some of the smaller words, but, patients arrive on the upper left. They each have characteristics like their ESI or, what their severity is. That arrival is based on historical patterns that we've seen. We randomize, a Tuesday at 8 o'clock, 3 people will show up, maybe Tuesday at 8 o'clock next week, 7 people will show up. It's all driven by randomization, but rooted in historical data. They hit the waiting room. They have different pathways they could go based on an assignment, a random assignment that they are appropriate for the PIT pathway. They should see a provider in triage or they should not. Which bed they should wait for. Is their bed open? If their bed is not open, they'll go to a different bed. There's a pathway for left without being seen, which says that they've waited so long that they have eclipsed some sort of random number we've assigned to them. Once that has happened, they are left without being seen. They exit the ED. There's EVS turnaround time for turning over beds. There's the rate at which bed patients can enter a unit. The faster they can exit the unit is dependent on the number of staff that's there to take care of them. So if we reduce the staff, we can enforce bottlenecks. There's also boarding times, as Keith was alluding. The more people boarding, the slower their bottlenecks. Of course, that's also a random process rooted in historical data. At a high level, what we were able to do is represent a 1 year's worth of activity in the ED, which is 65,000 patients. We can cycle 65,000 patients through in about 15 minutes of real time. So we can try a staffing configuration, run it through the simulator, get results, and then make a different staffing configuration, run it again, so we can maybe do 7, 8 staffing configurations in a short while, save all of the results, and just review that data to help select a good decision for staffing. All right. Looks like we have a technical issue because this is a video that is going to play. Let me exit because we are good on time. I'm exiting, I'm resharing, and I'm moving on to another version of the presentation. Can people see my screen? Can Susan or?
Yeah, people should be able to see it, Asaf.
Yeah, I see your PowerPoint right now.
Okay. People can see my PowerPoint. They can see the slide peek inside the simulation.
Yep.
Okay, great, fantastic. All right. Sorry about that, everyone. Okay, live demo. Okay, so what I'm showing you is a video of two different snapshots of a simulation. One of a single simulation, one taken at week 11 of 52 weeks of virtual ED. I took a snapshot at week 11 and a snapshot at week 17. The data is all real data from the simulation, and I just and then I was able to sort of turn it into a graphic that just showed patients moving around. So let me just play that. Okay, so it starts at 6 a.m. and we've got two different weeks. One row is a week, 1 week, and the second row is another week. And we got the waiting room, the acute unit, the forward flow, and the fast track. Each dot is a patient. The color is how sick they are. They arrive in the waiting room, and when they're able to, they are moved into their next unit. And the units open and close based on a time. So as at this moment, they're all open. They started out actually forward flow and fast track were both closed. And then so we can see the weeks 11 and week 17 are sort of behaving differently. Week 17, now it's 3 p.m. and week 17 has 2 left without being seen. That's the red stars. And this is, the rules governing both of these weeks are identical. It's what we're seeing here is a random process that created a pretty bad week 11 and a pretty good week 11 and a pretty bad week 17. And so that is just the fact of life of the ED, where not 2 days are the same. It sort of highlights how difficult it can be to run a 1 or 2 day experiment. You're at the mercy of these variances. And so yeah, week 17, by the end of it, there were looks like 5 left without being seen as we're approaching 2 a.m. on the next day. Just seeing those patients really pile up in the waiting room and then start leaving is a real stressor. Okay. Let me jump back into presenter mode here. Okay. People can see my HUP ED digital twin validation results.
Yeah, we're back.
Great, thanks. Okay, so what we do is after we build these simulations, we need to validate that we can believe and take action upon the results that are come out of it. So 2 different styles of validation that we do is we have can we recreate real life with our simulation. So here we have at the top is we have the waiting room census. How many people are in a waiting room over the course of some time period, and the blue line was like what we actually observed, and we observed this diurnal pattern. People sort of pile up into the waiting room on average midday into the early evening, into the early morning. And then, early morning, it's empty. And then so our simulator can create, waiting room census that is, pretty darn close to real life. That gives us confidence that that what we're doing is doing something that represents real world. Another form of validation on the bottom is that we're actually able to introspect the mechanisms of the ED in really fine detail. And so we're able to see that a bed census, the blue line is the bed census at a given unit, and the green line is the waiting room census. And we're actually able to see that as the waiting room census builds up, that we can then create left without being seen events. And so those left without being seen events are really tied to that waiting room census as it should be. And it looks like it happens at sort of the downslope of the census into the late evening, early evening into the early morning. with these really defined cluster events where things get sort of out of hand due to this just some, bottlenecking, sort of like a highway, and then the left without being seen events occur. They don't occur when things are moving very smoothly, and that matches our expectation. All right, I think we're going to pass this on to Keith.
Yeah, so I'm going to talk for a second about the real world use that we've had with this. But I have to say before that, how cool is that video? I mean, I saw that for the first time the other day, and it just kind of knocked my socks off. I'm an ER doc, and like heart attacks and gunshots and stuff doesn't faze me. But when I see the code that a software writes to do this, like I get palpitations. So it kind of highlights the importance of marrying, the data science with the clinical knowledge. So we've used this a number of times in real life. The autumn and winter were challenging for us. Coronavirus was kind of on the downslope. Normal hospital operations were on the upslope. For many complicated reasons, we noticed that our left without being seen rates were starting to creep up, which again threatens those principles of access to care. So we decided we wanted to do some experiments to see if we could drop those left without being seen rates back down. We ran, 7 or 8 experiments in the digital twin. We picked a couple of them to run in real life, and this is probably a good time to say, there is qualitative feedback from running in vivo experiments that you can't get from the digital twin. So that's an important thing to note here. But we settled on an option and actually adjusted physician scheduling and physician deployment to specific units within the emergency department starting on March 1st. And thus far, it looks like it's successful. We've only been in this new schedule for 3.5 weeks, so it's a little bit early to do a data analysis on it. But it looks very promising that we're going to be able to drop our left without being seen rates by somewhere between 0.5 percentage point and 1 percentage point. Now that may seem like a small number, but I'm going to start out by giving some context that we're starting at a pretty low percentage, so it's hard to make big gains when you're already doing well. And also say that if we extrapolate out to a year, this means that we would have somewhere between 60 and 120 additional admissions to the hospital per year, which would translate to increased revenue of somewhere between $200,000 and $500,000, which for our departmental budget is a not insignificant sum, and certainly will make a difference to being able to support those other aspects of the mission, like the educational mission, for instance. So it's really exciting to use this in real life and see some very promising results at this point. If we can go to the next slide.
Can I jump in for a second here? I remember when you first said this, I was thinking, well, if there's not that much, if you're doing really well, how much is there to improve? And I just want to point out that what you want to do is sort of maintain or improve while being able to move around your staffing to optimize staffing. I think I just wanted to point that out.
Yeah, that's a great point, and maybe this is a point where I can also say, operational experiments are impure and dirty by nature, right? Real world throws us a lot of curveballs that mean that we're constantly adapting. So a great example is, I'm sure many of you may be aware, or there's an article in the Inquirer this morning about it. HUP, took over this what was previously Mercy Philadelphia at 54th and Cedar, and is now operating that as an extension of HUP, which just went live yesterday, actually. And as a result, we had to redeploy staff out of our emergency department to support their emergency department. Now, that was not part of the initial digital twin experimentation. It was not part of our staffing plan, wasn't part of our goals for our fiscal year, but that's life. Things happen and you get curveballs. And instead of having to make a decision sort of blind about, well, where's the best place to pull staff out of the HUP ED to send over to the Cedar ED, we used the digital twin to say, okay, of all of these options, which is the option that's going to hurt the least for the HUP ED and let us maintain our numbers as good as possible while getting people over to the Cedar ED so we can staff over there. So that's the, I think we have on here the second bullet point there, the HUP 54 staffing impact. Is an on-the-fly thing that we use the digital twin for, which, the broader point here is the digital twin allows for making much better decisions, whether you're doing a real life experiment or not doing a real life experiment. It allows you to make decisions based on predictive analytics of an incredibly complex system where the cost of making a bad decision or a wrong decision is extremely high, both in terms of financial cost to the department, as well as cost to patients in terms of things like wait time, quality of care, et cetera. So, some of the impact we see here has the potential to be financial, but a huge amount of it is just making more informed and better decisions where previously we were making blind decisions. And the rest of this slide kind of lays out, we've used this to simulate and model other staffing changes in the department. So it's been amazing for us since we validated the model. We've used it 5 times in less than 6 months to inform our decisions. I think, Asaf, the next slide is yours.
Sure, thanks, Keith. Yeah, so, overall, we think that the digital twin is feasible and impactful for Penn Medicine. That this is something that we have built it, we are using it in one space, and we can use it in others. There are, however, going to be some prerequisites for making a successful collaboration and successful team. We really need well-engaged and knowledgeable operational owners, which Keith really fits the bill. This is someone who can define and speak about the workflow and help us validate the data and define those KPIs really well, so and hold us to it, so that we are able to delve in, to represent something that's real. That there's a real version of this, and we are building we're building to that real thing. We're as best we could. We also need data specialists. We have a very helpful, important member, Vince Collins, on our team, who is really quite knowledgeable about the data in the ED, and could really help supercharge this whole process by being a team member, not just handing over data, but actually being a team member to review, to help guide us and to validate. And not having those things really puts you in the hole. Not having that clear vision of what things are, what we're fixing, and where it's broken and where the data is. It's really important. And then, of course, we have the rest of the team, and myself, Susan Regla, myself, Corey Chivers, Mike Jagelis, people I'm not forgetting to mention, who each bring their own point. So operational owners, data specialists, and the predictive healthcare team, they really are sort of needed to work highly collaboratively together to drive this through.
So I think that that about wraps up our talk. These developments are super exciting. Like I said, the digital twin is letting us make better decisions, both when we have the ability to do in vivo experiments and when we don't have the ability to do in vivo experiments. And as the operational world that I live in is full of frequent and fast-paced changes and trying to adapt to really challenging circumstances, and being able to model a year's worth of emergency department flow in 15 minutes in the digital twin is an incredibly powerful tool to make better decisions and avoid costly decisions. So I think it's an incredible tool. It's been a really fun ride for me along the way to work with the data science team and everyone and learn how this works and get a little insight into things that I know nothing about. So it's been great, and I think it's it's helped us and has the potential to help other entities across Penn. Mike, I don't know if you joined, if you have any comments you want to add to this.
Yeah, unfortunately, I don't think we're able to get Mike. He's here as an attendee, but he's been muted as a consequence of the technology. Apologies for that.
All right, well, Corey, you're the producer, I guess, of this show. So are there questions? You want to moderate a discussion?
Yeah, for sure. So a couple questions came in, and I'll actually start us off with two. I'll combine two of the questions. I think they're related. But it was really around, we know that the digital twin is something that is, the concept is made available by some vendors, and I'm sure some people are thinking of which ones in particular. But what sort of spawned, or what are the sort of trade-offs to think about when we're thinking about build versus buy? So we built this all internally and did this whole project. What were some of the things that needed to be considered when evaluating that? And then sort of what I think is relatedly, another question came in around how this was built for the HUP ED. What would be sort of the process and procedures for building this out for another entity, or even potentially another sort of context, non-ED?
Great questions. Let me start with this second question. So I think a couple of things that are really important, as Asaf and Susan pointed out, are you need a really tight partnership between your client, which in this case is me, the emergency department, and the data science team. And you know, I think Einstein said that if he had an hour to solve a problem that would save the world, he would spend 59 minutes figuring out the right question and then a minute answering the question. And that's sort of what our process was like. We spent months just refining the question that we were trying to ask and what do we actually want the model to do before we started, you know, getting data and coding and things like that. So that tight partnership is really, really important. And then of course, you know, you got to make sure that you have access to the right data, that you're considering the human factors, not just the data and the operational plan. So that would be my answer to that question. Is it's very doable, but it does require, you know, some dedication of resources by the client in terms of both an operational owner and a data analytics owner. Asaf, Susan, do you guys have comments on that?
Yeah, I would add to that. I think it's really important. People underestimate the need to get in and actually see what's happening in the environment that you're trying to simulate. I think people who are experts or in, and you know, Keith, you are an expert and you know the ED. But everything to you is just sort of, this is the way things happen. And taking people who are not in the environment, typically like myself and Asaf went and did observations, and seeing what actually happens sometimes lets you dig through assumptions that you start with and say, you know, we started, for example, with trying to look at whether people were assigning the severity of index. The severity score well and accurately, and it ended up that was actually working quite well. And I think it's really important to challenge your assumptions as you're going into a new environment and make sure that you don't just assume that the new environment is going to work just the way that the old environment, you know, the hub environment, for example, worked. Asaf, did you want to add?
No, you've answered very well. I think that I'll just probably just piggyback what you guys have said about the need to, you know, really engage and assemble a good team, and that would be a prerequisite even when working with a vendor. These simulation tools are not very rarely turnkey, and the better your question and engagement are, the better your result will be, no matter who you work with.
Yeah, and that makes me consider that first part of the question, which was the, you know, the homegrown versus the vendor. And you know, I should preface this by saying I do not have any personal experience working with vendors who offer this type of solution. That being said, you know, in the life cycle that Asaf presented, I think one of the slides early on kind of shows the life cycle of this. There's an aspect of continual validation, right? I mean, there are the simulation learns from data, but those data are changing in response to sometimes imperceptible and intangible and unknown operational factors. So the way that the simulation is today is not going to be predictive, for instance, when we move across the street into the new building, because it'll be a completely different care environment. So we're going to need to make tweaks to the model to ensure that there's high predictive fidelity in the simulation and the new reality in the new building. And that's an example of this life cycle where the model needs continuous validation. And I don't know if every vendor will offer the robust support necessary to do that continuous validation so that you always feel confident about the predictive fidelity of the model.
Great. So another question had to do with, you know, so you decided to use the simulation model to address questions of staffing and staffing configurations. What are some other kinds of questions, operational questions, that could be asked of a simulation type environment like this?
Sure. That all depends on what you teach the model. So an example that has been talked about is, if we expanded, moving out of the world of the emergency department into the world of the whole hospital, if we expanded elective surgeries to be 7 days a week rather than 5 days a week, what kind of impact would that have on the hospital? Would it be more efficient, less efficient, cost more money, cost less money? If we had built a simulation model to model hospital flow and surgical schedules, that's a question that we could answer without actually doing surgeries on weekends, which is, that's a tall order for surgeons and nurses and techs and patients. So that's an example that scales up, to much larger questions about hospital flow, much larger financial implications as well. The caveat, of course, is, like I said, you can only use the model for the things that you've already taught the model about. So it's difficult to ask, for instance, our simulation that we've built to completely accurately predict what emergency department flow will be like when we move into a brand new building. We can ask limited questions that try to answer that question, but I can't use this model to completely globally model our flow once we move into a completely new physical plant.
Yeah, so I'll just add a little bit to that. So, once in March when COVID hit, the volume of the census volume in the hospital dropped drastically, which had at least the only positive impact in so far known to man, which is that the boarding time in the ED actually also went down because there were available beds in the hospital, and so we were actually able to use that observation as part of our validation scheme, where we were able to turn down the amount of boarding that we assigned to patients, and actually able to replicate, some key metrics coming out of the ED into how full the beds would be and how full the waiting room would be, to match like the basic COVID period in March to May, where the hospital was very quiet. So that's the kind of question we can answer. Hypothetically, boarding goes down in the future for some reason. I won't answer how that is done because people have thrown out a lot of brain power at that. But if it were going to go down, this is what it would look like in the ED. If it got a lot worse, this is what it would look like in the ED. But we can't ask those kind of questions.
And to piggyback one last comment on that topic, we've mentioned boarding in the emergency department a few times, which if I have my emergency department medical director hat on, that's not something I like, right? But if you put on the hat of a higher level hospital executive, you would say, well, I might tolerate a certain level of boarding in the emergency department in return for making sure that I can take care of the oncology population and meet their needs, and take care of the surgical populations and meet their needs. And if we took the time to build out a simulation for the entire hospital, which is a exponentially more complex entity than just our department, we could try to make predictions about bed allocation and human resource allocation within the hospital, understanding what our thresholds were for tolerance of things like boarding in the emergency department, the waiting list on the oncology schedule, and things like that. So this is the emergency department use case is in some ways sort of the tip of the iceberg here.
Yeah, excellent. Yeah, I mean, I totally see this as being, it's a great big what if machine, right? That can any kind of what if questions, scenarios you can come up with, what might be the impact of this complex intervention. These are the kind of questions we can answer, especially when they're the result of some interlocking process that has non-obvious sort of implications for changing one thing on what will happen downstream. This is great, and so a lot of answers actually to some of the other questions that have been asked have already sort of come up in these discussion. But another interesting one that came in is kind of around other approaches. So I started this talk with the idea that normally predictive healthcare we're thinking about like using machine learning on individuals to predict things like what's this patient's ESI going to be, or what's their length of stay going to be, and we could have thought of using those kinds of tools to tackle some kind of a project in the ED. Going back to the beginning of the project, how did the team decide that sort of staff planning and that process with the digital twin was kind of the best initial approach to the sort of, let's call it the overall problem of ED operations management, of which I'm sure there are many problems.
I'm not sure I 100% understand the question. Is it how do we decide on these specific goals, or how do we decide that the digital twin is the right tool to address those goals?
Yeah, I think the questioner is trying to get at how, there's improving ED flow in some way, or, if the goal is, keep left without being seen at some low rate, there's any number of levers one might pull to be able to achieve that. And then given whatever those levers are, any number of tools that you might use to try to affect those levers. So it could be by having a better prediction of patient ESI when they come in, may somehow smooth flow. And I know, from being there in the project, some of those things were sort of discussed as potential projects to undertake to generally tackle this problem of ED flow, optimal ED flow. So I think they're kind of interested in how this sort of using the staffing model and using the digital twin as the approach was sort of decided on as the angle to take here.
Okay, I guess my answer is that in reality, the number of levers we had and the ways that we could pull on those levers were not as extensive as perhaps one might think. So we had already done a massive overhaul to the general flow model through the department, which is based on best practice nationally, having expert consultants come in and guide us through that. Once the new flow models were set up, the question really became, what's the best way to deploy our staff in these 3 different units or 3 different care tracks within the emergency department? And that question, I suppose we could have gotten at that by saying, well, just look historically at acuity data as represented by that ESI level. The trouble is that ESI level is doesn't have the predictive ability we would like for things like length of stay and resource requirements during their time in the emergency room, and that this approach models the far more complex and emergency department environment with much greater accuracy than just relying on 1 or 2 or even 3 characteristics of patients. Just doesn't get you the predictive fidelity you need because it's such a complex system. Whereas the model that we've built does a much better job with predictive fidelity in such a complex system. So I'm not sure that I've completely answered the questioner's concern, but you can always feel free to shoot me an email and I'm happy to talk about it more.
That's great.
Yeah.
Susan, did you want to jump in?
Yeah, I just would refer, and I think that this is relevant to this question that I mentioned. The initial impetus to look at how ESI was being assigned, et cetera. And one of the things that we found in that is that it was really a combination of decision making between one section of the emergency room and another section of the emergency room, which was saying, okay, this person's been assigned as ESI 2, for example, but or 3, for example, but I think that they're a higher acuity than should be handled here. And so the number of those different collaborative decision-making things going on in the emergency room to do it at the individual patient level. It seemed, it was one of the reasons I think that we wanted to look at the system level rather than the individual patient level to see just how are people moving through, depending on what the decisions are, how are people moving through, and what happens if we tweak levers to make them move through differently.
Great. Okay, well, we're in the final minute. There was just one little technical question. Somebody wanted to know about Python modules being used and whether code for this is going to be available. I'll let Asaf tackle that real quick, and then we'll sing ourselves out.
Yeah, so Python modules actually all basic stuff. So it's really just pandas and NumPy. Nothing really fancy in here. It's pretty much built from the ground up. There are simulation modules that we're actually looking into, maybe shifting some of our code base into, like SimPy. We have not done that yet, but it is basically all basic stuff. Share code, I think so. It is on Git. It's in a private repo. I think sharing that is a goal to make that public, but it is not. It's right now. It's private.
Yeah, and my understanding is we're in the process of modularizing it and making it available as a pip installable type tool, and
Yeah,
that'll be when we'll be able to share it.
exactly. Yeah.
Okay, well, I want to thank the speakers for speaking today, and thanks everyone for attending. I think it's been a really great talk. I also got a lot of non-questions that were just sort of thumbs up and great presentation and comments like that coming into me through the side channels. So so very good, very well done, everyone, and thank you very much. Hope everyone has a great weekend.
Thanks, everyone.
Thank you, Corey. Thanks for organizing.
Yeah, thanks, Corey.
Thanks, everybody.
Have a great day.